Rogério Mol from Universidade Federal de Minas Gerais. He's going to talk about indices for holomorphic vector fields in the plane.
Thank you very much. Thanks for the organizers for the invitation. Well, my talk has this generic title, but I will talk about some indices of holomorphic vector fields, and I'll show how they relate to each other. In the beginning, I'll make some definitions. In fact, I'll make lots of definitions in my talk. I state some results, and I won't give any proof. So I talk about vector fields, holomorphic vector fields in the plane, germs of holomorphic vector fields with coefficients Q and P, which are germs of holomorphic functions, relatively prime. This means, since I'm talking about singular vector fields, singular vector fields, this means that the singularity is isolated. And I also talk about the dual form. They define the same singular holomorphic foliation at C2, 0. Well, I start by presenting two basic invariants, the order of the algebraic multiplicity, which is the minimum of the orders of Q and P, and the Milnor number, which is the dimension of the local algebra. Okay. Some of these indices, they are associated with invariant curves. So let me define a separatrix. A separatrix will be a germ of reducible formal curve. It's given by an equation, a formal equation, that satisfies this algebraic relation. F divides omega, which is the one form that gives the foliation, wedge df in the ring of formal functions. Well, if f can be taken as a holomorphic function, the separatrix is convergent or analytic. I'll denote by SEP the family of separatrices of f. Well, a singularity of f is said to be simple or reduced if the linear part of x, a vector field that engenders f, is non-nilpotent, has at least one non-zero eigenvalue, and the eigenvalues are such that their quotient is not in Q, in the positive rationals. A simple singularity has exactly two separatrices, which are smooth and transversal, corresponding to the eigendirections. In the non-degenerate case, both eigenvalues are non-zero, both separatrices are analytic. But if one eigenvalue is 0, we have a saddle-node singularity, then the separatrix associated to the non-zero eigenvalue is convergent. It's called the strong separatrix. And the one associated with the 0 eigenvalue can be purely formal. That's the way formal invariant curves appear. Well, we consider blow-ups, punctual blow-ups at the origin. And the foliation is transformed by this blow-up into a new foliation with finitely many singularities over the divisor of this blow-up. And this blow-up can be of two types. This is very important in the development of our work. It can be non-decritical if the P1, the divisor, is invariant by the transformed foliation. And it's decritical if the divisor is not invariant. So it's fibered, generically fibered, by leaves of the transformed foliation. Note that all these leaves, when they are blown down, they become separatrices down here. So a decritical blow-up engenders infinitely many separatrices. And there's a reduction of singularities. Okay, I can find a sequence of blow-ups such that the transformed foliation has a finite number of singularities, all of them over the divisor, all of them simple. The transformed foliation is everywhere transversal to the critical components of the reduction divisor. Two critical components do not intercept, and this sequence is minimal with these properties. And this reduction of singularities is unique up to isomorphism. Okay. I would say that the foliation F is non-critical if all blow-ups in the reduction of singularities are non-critical. This is equivalent to saying that all components of the reduction divisor are invariant by the transformed foliation, and which is equivalent to saying that the separatric set is finite. And is critical if some blow-up is critical. This means that there is a component in the reduction divisor invariant by the transformed foliation, which is equivalent to saying that the separatric set is infinite. Now, I'll give a definition of a family of foliations. We say that a foliation F is a generalized curve foliation if there are no saddle nodes in its reduction of singularities. Well, it's a definition by Camacho, Linsneto, and Paulo Sade. Well, generalized curve foliations are very well behaved. People in the theory of foliation, they love these foliations for many reasons. Okay? The separatric set only contains analytic separatrices. There are no formal separatrices. The singularization for the separatric set is a reduction of singularities for F. The mu number is minimal considering all foliations with a separatric set in the same X singularity class of the separatric set of F. And this concept is invariant by topological equivalences. If another foliation is topologically equivalent to F, and F is a generalized curve foliation, then F prime is also a generalized curve foliation. And besides, they have isomorphic reductions of singularities. Okay? Now, generalized curve foliations, they don't have saddle nodes. So what happens if I allow some saddle nodes? Well, a saddle node has a formal normal form of this type, okay, where lambda is in C and k is a positive integer. This number k plus 1 is called weak index. It's always bigger than 1. And I say that a saddle node is tangent. Well, I have a foliation, and I have the singularization for it, a reduction of singularities. So I say that a saddle node is tangent if its weak separatrix, the one associated with the 0 eigenvalue, is contained in the reduction divisor of D. For example, if I have a saddle node in the crossing of two components of the reduction divisor, it's necessarily tangent because well, its weak separatrix is necessarily contained in the divisor. And the first index I introduce is this, the tangency excess of F. It's defined this way. It's a sum where here I put the weak index minus 1. So it's k here, which is positive. This row here is the weight of the divisor. The sum is over all tangent saddle nodes. dq here is the component of the divisor that contains the weak separatrix at q. And this rho is the weight of the divisor. It's the order at the origin of an analytic curve whose transform by sigma touches the component dq transversely outside a corner. So that's, we can see here that this number is positive whenever I have a tangent saddle node. If there are no tangent saddle nodes, by definition, this number is 0. Now, I define another family of foliations that contains that of the family of generalized curve foliations. And the foliations of second type. We say that F is a second type foliation if there are no tangent saddle nodes in its reduction of singularities. It's a concept introduced by Mattei and Salin. These foliations are also well behaved. They have some properties. First, the singularization for the separatrix set. Remember that now, since I have saddle nodes, these foliations may have purely formal separatrices. Okay? So the singularization for the separatrix set is also a reduction of singularities for the foliation. These foliations, they minimize the order or the algebraic multiplicity, considering all foliations with separatrix set in the same X-singularity class of the separatrix set of F. So generalized curve foliations, they minimize the Milnor number. Second type foliations, they minimize the order. And they can be identified by this invariant I have just introduced, this tau, this tangency excess. F is a second type foliation if and only if tau is 0. It's by definition. Tau is 0 if and only if there are no saddle nodes. Tangent saddle nodes, I mean. Concerning second type foliations, have the following results, which I proved in collaboration with Rudy Rosas. If I have two C-infinity equivalent germs of foliations, then this number, this tau, this tangent excess index, is the same. So it's C-infinity invariant. And now, concerning second type foliations, if F is a second type foliation and F prime is a germ of foliation C-infinity equivalent to F, then F prime is second type. And both foliations, they have isomorphic reduction of singularities. Okay, it's a weaker result than that for the corresponding result for generalized curve type foliations. And the point here is to use this C-infinite equivalence between the two foliations to send a formal separatrix of one foliation into a formal separatrix of the other foliation. Now, this result I present is, in a certain way, the inspiration for the rest of my talk. This theorem was proved by Marco Brunella. Let F be a non-decritical germ of foliation, let's say 2, 0. And let S denote the union of all its separatrices. Non-decritical means a finite number of separatrices. Then F is a generalized curve foliation. If F is a generalized curve foliation, then I have these conditions here. BB is equal to CS, and GSV is 0. So BB here is the Baumbot index. CS is the Camacho-Sad index with respect to the invariant curve S. And the GSV stands for the Gomez-Mont-Sead Everjovic index with respect to this invariant curve S. So I'll give very brief definitions of these indices. And our objective is to find characterization in terms of indices for foliations of second type. Okay. First, the Baumbot index, I have the vector field that engenders the foliation. It's defined as the residue. Here I have the square of the trace of the Jacobian matrix of Q minus P over Q times minus P. Okay. It's this residual, Grothendieck residue. Okay. I'm not worried with how to calculate them, properties. I only state some properties of this index and how they relate to each other. And now, the CS index and the GSV index, they are associated with invariant curves. So how can I calculate them? Suppose that f is defined by the one form, by this one form, and C is an F-invariant analytic curve with reduced equation F. So I can find a decomposition in this way. I can find functions, analytic functions, G and K, and a GM of analytic one form, eta, so that G times omega is equal to K dF plus F eta. And I use this decomposition to calculate these two indices. Okay? The question, my problem here is that I have invariant curves which are formal. So I have to find a way to calculate these indices for formal invariant curves. And for this purpose, I use formal decomposition. When this invariant curve C has purely formal branches, there is a formal decomposition. I find G, K, and eta formal, associated with the formal equation of the curve. Now, the Camacho-Sad index is this integral over the link of C of eta over K that appear in the decomposition associated with this curve. Okay? It's used to prove that this definition doesn't depend on the decomposition, on the equation of the foliation, on the equation of the curve. Okay? It's well defined. We can also prove using this definition that there is an adjunction formula. The CS of a union of curves, of F-invariant curves without common branches, is the CS of the first curve plus CS of the second curve plus 2 times, here I have an intersection number of these two curves. And when I have a formal branch, what can I do? I can take, well, I have a decomposition. I get a Poiseuille parameterization of this formal branch. So I pull back this one form, eta over K, to C, and calculate the residue of this one form. This gives a formal CS index. And for a curve of separatrices containing some purely formal branches, I can define the CS using that adjunction formula. For the GSV index, the definition using the decomposition is this: integral over the link of C of G over K d K over D. Okay. The adjunction formula reads GSV of C1 union C2 is the sum of the GSVs minus 2 times the intersection number. And for a purely formal branch, I do a similar thing. I get a Poiseuille parameterization for the formal branch. I pull back this one form by this Poiseuille parameterization and calculate its residue. And for an invariant curve containing some purely formal branches, I use the adjunction formula to define the formal GSV. Now, another index that does not appear in the statement of Brunelles's theorem. Well, I have a foliation and a small puncture neighborhood of the singularity of the foliation. Here at this point Q, F is regular, so I can find a holomorphic one form zeta at Q such that d omega equals to zeta wedge omega. It's very simple to prove this. Another one form zeta prime coincides with zeta over every leaf of f. So in this way, we define in this puncture neighborhood a multi-valued one-form zeta, which is called exponent one form, which is single-valued when restricted to each leaf of f. And they satisfy this equation. I need this exponent one form to define the variation index due to Canedani and Sua. Well, I integrate over the link this one form, this exponent form. And now the variation index is very well behaved when it concerns to union of invariant curves. It's additive. The variation of C1 union C2 is the sum of variations. I have no more adjunction. And it's related to the two previous indices. Variation equals to CS plus GSV. This was proved by Marco Brunello in that paper I cited, that result. And in order to define the variation for an invariant curve C contained purely formal branches, I use this formula. I have a definition for the CS, and I have a definition for the GSV for formal invariant curves, so I have a definition of the var. Now, these indices, which are calculated over invariant curves, I use the language of separatrices. Okay? Instead of talking about the index calculated in an invariant curve, I will talk about the index calculated on a divisor of separatrices. So a divisor of separatrices is a formal sum, it's a divisor, but I require that the coefficients are -1 or 0 or 1. Evidently, the coefficients are non-zero only for finitely many separatrices. This requirement is due to the adjunction properties of the indices. So I have the usual language, the support of a divisor. A divisor is effective if the coefficients are all non-negative. And we have the composition of a divisor into divisor of zeros and divisor of poles, the difference of two effective divisors. Okay. I also say that a divisor of separatrices is adapted to a separatrix B if B is contained in the support of the zero divisor. Okay. Now, another definition which is crucial for all the development I'll do later. A divisor of separatrices is said to be balanced if, first, the coefficient is 1 for every every isolated separatrix. Here. An isolated separatrix is a separatrix that, when I do the desingularization, touches a non-dicritical component, touches the invariant part of the divisor. So all isolated separatrices, they enter in this definition. They appear with coefficient 1. And I will also put some dicritical separatrices. For a fixed dicritical component, well, I have infinitely many separatrices cutting the dicritical component. The following equality holds. The sum of the coefficients is 2 minus the valence of the dicritical component. So the separatrices which are associated with the dicritical component are such that their coefficients, they satisfy this equation, 2 minus valence. Valence of D is the chemical valence. It's the number of bonds. Okay? Let me explain with a drawing. Here, this is a reduction divisor. In red, I have the components which are invariant by the transform foliation. The dashed circles are the critical components. So every separatrix that touches an invariant component will appear with coefficient 1. Here, I have a critical component with valence 1. Okay? So I have that number, 2 minus valence. 2 minus 1 is 1. So I have to, here I put one separatrix with coefficient 1. Here, I have a critical component with valence 1, 2, 3, 4. Okay? 2 minus valence is minus 2. So the sum of the coefficients must be minus 2. I put 2 separatrices with coefficient minus 1. Here I have a component with valence 2. 2 minus 2 is 0. I didn't need to put a separatrix here. So, but I can, for example, put separatrix, green separatrix with coefficient 1, and a blue separatrix with coefficient minus 1. 1 minus 1 is 0. I have the right to do this. Okay? Why this concept is important? Because it's a very nice and effective way to control the order or the algebraic multiplicity of the foliation. We have this result by Rogério. The order of F is the order of B, the balanced divisor of separatrices, minus 1 plus the tau, the tangent excess index. Okay. Now I still have to talk about another index. So I have to, which has polar nature. So let me explain what is the polar curve of a foliation. The polar curve of omega, in fact, this is a formal one form. P and Q, they don't need to converge. The polar curve of omega with respect to AB in P1 is the curve with this equation. Okay? I have the coefficients P and Q. If omega is convergent, it defines a foliation. In this case, the polar curve assembles all points where the leaf of F has a slope B over A. This drawing explains what a polar curve is. Here I have a foliation, okay? Have the lines, the pencil of lines with slope B over A, and I assemble all points where the leaf of the foliation has tangents, it has tangent line with the slope B over A. So here I have a component of the polar curve. Maybe we can find other components here. And I use polar curves to define another index, another invariant, which is the polar intersection number. Well, the polar intersection number of this one form with respect to B is a separatrix, a formal invariant curve, is the intersection number of the polar curve and B, okay? But calculated for a generic point AB. For generic AB, this number is constant. It's called the polar intersection number. Okay, and for the divisor of separatrices, I define this polar intersection number additively. For instance, here I have this proposition I proved some months ago. If I have a balanced divisor of separatrices for F, then the polar intersection number with respect to the balanced divisor is the Milnor number plus the order of F minus this number tau, which counts, essentially it counts the tangent excess indices along the infinite linear points to a generic polar curve. In particular, this number is 0 if and only if the foliations of second type. So for second type foliations, we have that polar intersection equals Mueller number plus order, algebraic multiplicity. So now, another index, the polar excess index, this delta index. I do the following. I have a germ of foliations, a balanced divisor of separatrices. Here I have B separatrix, so I get a balanced divisor which is adapted to B. B is contained in the support of the zero divisor of B. And I got here a formal meromorphic function whose divisor is B. It's a formal equation for the balanced divisor B. The polar excess index with respect to B is the integer. Here I calculate the polar intersection of F with respect to B and the polar intersection of dF. That's why I had to define the polar intersection for a formal omega, okay, with respect to B. It's the difference, this difference. Okay, and for divisor of separatrices, I define the polar excess in an additive way. Okay. Here. So the fact is that this index, it characterizes generalized curve foliations. You see that whenever I have an effective divisor of separatrices, this delta is non-negative. And if B is a balanced divisor of separatrices, so the foliation, then F is the generalized curve foliation, if and only if this delta index, this polar excess index, with respect to the zero divisor of B is 0. Okay, so it gives a characterization of generalized curve foliations also for the critical case. And, well, this index, this delta index, is related to the GSV index. If I find an effective divisor of if I have an effective divisor of separatrices and B a balanced divisor adapted to this effective divisor, this means that this effective divisor is contained in B0, then the GSV with respect to C equals delta with respect to C. And here I have this intersection of C, B0 minus C intersection with the divisor of poles of B. So this term explains why the GSV can be negative in the critical case. In the critical case, we may have a non-trivial B infinity here, and this may the delta is always positive. It's always non-negative, but the GSV can be negative. These results were proved by myself and by Johann Gesmer. In the non-critical case, the divisor of separatrices equals to its zero divisor. And support is the whole separatrix set. So as a consequence, the GSV equals the delta. In non-critical case, the GSV calculated with respect to the divisor of separatrices, balanced divisor, is the delta index. So F is a generalized curve type if and only if the GSV with respect to B is 0. This was already known by Brunello. Brunello had proved one direction, and Daniel Alemán and Vincent Cavalier proved the other direction. What happened? Okay. Now, I define the total index. The total index, the total var, and the total delta will be defined as the var calculated with respect to a balanced divisor of separatrices, and the total delta will be the delta calculated with respect to a balanced divisor of separatrices. And in the non-critical case, I can also define the total CS index and the total GSV in the same way. The total CS will be the CS calculated with respect to the balanced divisor, and the same for the GSV. In the non-critical case, I still have the total var is the total CS plus the total GSV, and the delta equals the GSV. Now I can state the main result of my talk, which I proved in collaboration with Arturo Fernando Pérez, and the result that makes a relation among all these indices. So I have a holomorphic foliation at the origin of C2 with no hypothesis at all, only holomorphic foliation. This encompasses both the dicritical and non-dicritical case. Then the Baumbot index equals the total variation index plus the total delta index, and plus here I have a correction term, which is the sum of the squares of those taus, the excess of tangencies, the invariant that counts the tangent saddle nodes along the infinite linear points of F. Okay. And let's return here. This number is 0 if and only if F is a second type foliation. Okay? So I have a characterization of second type foliations in terms of indices, which I proposed in the beginning of my talk. F is a second type foliation if and only if the Baumbot equals the total variation plus the total delta. In the non-dicritical case, this equation becomes Baumbot equals CS plus 2 times GSV. The non-dicritical case, the var is CS plus GSV, and the delta is the GSV. Okay. In particular, F is of generalized curve type if and only if the Baumbot equals the CS index. Okay. Because generalized curve type in the non-dicritical case is equivalent to saying that the total GSV is 0. Okay, I still have 1 minute. So just 1 minute to talk about the proof. The proof is we calculate these indices for reduced singularities. The calculation are in this table. This is an easy task. Okay. Here is for a non-degenerate singularity with eigenvalues lambda 1 and lambda 2. For a saddle node, these indices are in this table. Okay. And we do an induction in the reduction process. Okay. Because we can control how these indices they behave by blow-ups. We have formulas, known formulas. Okay, and we also have formulas, results of global nature. We need these results whenever I have a blow up and an invariant component, a non-dicritical component, because I introduce new separatrices. So I need these also results of global nature for these indices. In the process of induction, I proved that theorem. Okay, only this. So. On time. Thank you very much.